Welcome to example number 4. We have a soap film here that is a thickness T of 375 nanometers. And we have this is coating a layer of glass. So we have the incident light, the sunlight, coming through here through air, and then it comes into the soap, 1.33, and then it goes into glass. So there's refraction occurring here. So now they don't show the beam going through here as well, and the reflection going through here. Because what we're really considering is what is happening between ray 1 and 2, and they're interfering with each other. What we're asked to find is for which wavelengths of light will we get constructive interference. So what colors will that person see from this scenario? Okay, so we're going to start off by writing our extra path difference is equal to 2t, because it's going to go up and down, plus the net phase inversion. And what we need to decide is what the net phase inversion is. Now the net phase inversion, we need to look at the reflections that occur at the first barrier here, and we're going from less dense to more dense. We're going into medium where light is slowing down. And in this type of reflection here, we get a 180-degree phase shift for that ray 1 because you're going from less dense to more dense. Then upon this reflection at the bottom interface, we're going from less to more once again. So this also will go through a 180-degree phase shift. So if you look at the relative phase shift between these two rays, there is no difference between them because they both went through the same phase shift. So in this particular case, the net phase inversion is 0. So we can rewrite this extra path difference as just simply 2t. Next, we want to know what to set this extra path difference. We're told that we want constructive interference, and hopefully you recall that if you want constructive interference, then these rays must differ by a multiple of the wavelength. So we're going to replace extra path difference with m lambda equals 2t. Next thing we need to use is this wavelength that we're looking for, the wavelength of the light in the air. Now we can solve for the lambda in the film, but what we're looking for is the lambda that this person's going to see in the air. So what I'm going to do is I'm going to replace this lambda in the film with lambda in the air. So lambda in the film is equal to the lambda in the air divided by the index refraction. Now which index refraction do we use? Air, soap, or glass? And we look at here and we can see this is where the extra path difference is occurring, going down and back up, so it must be the wavelength within the soap. So this is n soap. So we can replace that into this equation and have m lambda air divided by n soap equals 2t. And we're solving for the lambda in the air. So lambda in the air will be equal to 2t times the index refraction in soap divided by our order number m. Now we're looking for what light you can visibly see, and if you recall, hopefully, the wavelengths of red, which is the longest wavelength, is roughly around 700 nanometers, and the wavelength of, say, violet is roughly around 400 nanometers, around that range, maybe 450, I can't remember exactly. So we can only accept wavelengths that are in this range, otherwise our eye won't see it because we only can see within that range. So what we do is we basically go through trial and error. So we set, for example, n equal to 1, and you solve for lambda in the air. You'll have 2 times the thickness, which is 375 nanometers, times the index refraction within the soap, which is 1.33, divided by 1. And I get a wavelength of 997.5 nanometers. And if you look that up on the internet, you'll find that that's in the infrared range. So that's not possible. So then we move on to m equals 2, and we solve for that. We have 2 times 375 nanometers times 1.33, now divided by 2, and you get 499 nanometers, and this is green. So great, we see that one, that works. Okay, the other one didn't work. And then we can see, maybe we see other ones, so we set m equals 3 in here and solve for lambda air, putting in same thing, except you're going to replace 2 now with 3, and you're going to get 249 nanometers, which doesn't work out because that is near the UV range. So the only one that we see is the 499 nanometer wavelength of light, and that's what this film will produce at this particular thickness. Now, usually in a thin film you might get all sorts of thicknesses, and so you might get a bunch of different colors that you'll see. Not just, you'll see sort of a green band and maybe a blue band and a red band, depending on the various thicknesses. Okay, and that's it for example number 4.